Hello, myself Dr. BJD Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss regarding floating point representation and arithmetic. At the end of this video, the student will gain knowledge regarding how floating point numbers can be represented with examples and how various arithmetic operations like addition, subtraction, multiplication, division can be performed with the help of algorithms on the floating point numbers is discussed. And the topic learning outcome is mapped to the course learning outcome of make use of number system for data representation and binary arithmetic in digital computers. The topics that are discussed in this video are introduction, floating point representation, floating point addition and subtraction, floating point multiplication, floating point division. The floating point representation can implement operations for high range values. Generally, the engineering and scientific applications can require the floating point representation. So, the numbers can be represented in the base multiplied by exponent form can be used to represent the scientific notation for large computational incentive applications. So, the floating point representation can implement operations on high range of values. So, the numerical evolutions are used to carry out using floating point values. So, to calculate easily and to represent in scientific notation, the floating point numbers can be represented as one mantissa multiplied by base to the power exponent. So, here, for example, if you want to represent the large number into the scientific number, the base value can be 0.56. In this example, 10 power 7 can be used to represent the scientific notation. So, here 0.56 is the mantissa and 7 is the exponent value. So, the numbers can be represented in this way, the scientific notation. So, the binary numbers can also be described in exponential form. So, the description of binary numbers in the exponential form is called floating point representation. So, each number can be represented with mantissa multiplied by base power the exponent value. So, the mantissa can be represented with a letter m and the exponent can be represented with a small e letter. So, if the binary numbers are represented in this exponential form, those representation is referred as the floating point representation. So, the floating point representation breaks the number into two parts. The left hand side is the signed fixed point number. So, that number is known as the mantissa. And the right hand side of the number is known as the exponent value. So, there are basically two important points to represent the floating point numbers. Those two parts are the mantissa and the exponent e. Mantissa can be represented with the letter m and the exponent can be represented with the letter e. The two parts represent a number generated from multiplying m times a radix raised to the value of the exponent e. So, here the basic representation of floating point can be m multiplied by r power e. Mantissa multiplied by radix power exponent. This is the basic notation of floating point representation. So, in order to represent the sign bit can be used. So, here the plus or minus the sign bit, it can be represented with the 0 or 1. If 1 is present, then the sign bit of the number can be 1, then those numbers can be the negative numbers. So the basic notation can be the sign bit representation to denote whether the number is positive number or negative number, and m is mantissa or significant, multiplied by base or radix to the power plus or minus exponent. So here 3 parts majorly used to represent the sign of the number, the mantissa, the exponent. Now we have to describe how to convert the decimal number into floating point number. So this process involves the 3 steps. One is take the integer part of the number and generate the binary equivalent. So the decimal number integer part can be taken and it must be converted into binary equivalent. So the decimal number can be converted into binary equivalent by dividing the number with 2 value until it cannot further divisible. Whatever remainders that are obtained can be written in bottom to top approach. In this way, the decimal number can be converted into binary number. For example, if you take a value 10, this can be divided with the 2. So 5 2's 10, remainder 0. 2 2's 4, remainder 1. Again this number is divided into 2, 1, 0. So the one which cannot be further divisible. What are the remainders that are getting? Those can be written in a top-down fashion to get the binary equivalent of the decimal number. So the integer part of the number can be used to generate the binary equivalent by using this continuous subtraction method, continuous division method. With the base value, the number with the base value of 2, the number can be divided and the remainders can be written in top-down fashion to get the equivalent binary number. Next, take the fractional part and generate a binary fraction. So here we have to represent the fractional part with after point. What is the decimal number positions can be 2 power minus 1 plus 2 power minus 2, like that. The decimal fractional part has to be represented in binary form. Then place the 2 parts together and normalization can be performed. In order to perform the normalization, the mantissa multiplied by radix power e form has to be used to represent and to normalize both the parts. So these are the steps that are involved in converting decimal number into floating point. Now consider an example how this decimal number can be converted into the floating point. So here the mantissa, the integer part of the number can be considered during the first step. So here the number that is considered in the example is 6.75. The 6 can be represented in the binary equivalent form. So here we can use the continuous division method and whatever remainders we can get has to be represented in the binary fashion. So the 6 binary equivalent can be 110 in the binary equivalent form. So this is the end of the first step. During the second step, the fraction part has to be taken and multiplied with 2. So whatever the integer part that can be written taken as the fractional part of the binary equivalent number. So 0.75 multiplied by 2, 1.5. Here the integer part is 1. 0.5 into multiplied by 2. So here it is 1.0. The 1 can be taken. 0.11 can be the binary equivalent of the fractional part 0.75. Why? Because whenever the after decimal point in the binary, positions can be obtained by multiplying with 2 power minus 1, 2 power minus 2, like that the positional values. So the integer part and the fractional part can be represented, integrated and represented. Put the two parts together. The 6 equivalent is 110. Point, the fractional part is 1 1. So this is the both parts can be combined here. Then after the step, the normalization can be performed. So here it can be normalized as 1.1011 into 2 power 2. So here 1.1011 is the mantissa, radix is 2, and the exponent value can be the 2. So in this way, the decimal number can be converted into floating point number. So here it has to follow 3 steps. One is take the integer part of the number and generate the binary equivalent. Take the second step, take the fractional part and generate a binary fraction. Next, place these two parts together and normalize in order to represent mantissa multiplied by radix power e value. So IEEE can establish a standardization in representing the floating point numbers. So the IEEE, Institute of Electrical and Electronics Engineers, is an international organization. So it is used to design specific binary formats for storing floating point numbers. So the standard way of representing floating point numbers is notated by using the IEEE standard. The IEEE defines two different formats with different precisions. So two categories are there to represent the floating point numbers. One is single precision and double precision. So double precision can be used by double variables, and in a C, if you are observed in a C programming language, while defining the data types, we can have different categories like int, char, float, double. So here the decimal numbers can be represented with two data types, float and double. The float can be generally the single precision format. Double is the double precision format. So these double precision are generally used by double variables in the programming languages. So the memory occupation of these data types can be deferred by using the single precision and double precision representation. So IEEE 754 representation can be used to represent the floating point numbers. So here the first part that can be represented can be the sign of the mantissa. So the sign bit can be either 0 or 1. If it all 0, then it represents the number is a positive number. If it all the sign bit is 1, it represents the number is a negative number. And the biased exponent, the exponent field need to represent both positive and negative exponents. A bias is added to the actual exponent in order to get the stored exponent. So that can be represented with E value. Next, the normalized mantissa is the other part of the representation. The mantissa is part of a number in scientific notation or a floating point number. So it can consist of significant digits. So here we have two digits, either 0 or 1. So the normalized mantissa is 1, which only 1 to the left of the decimal. So here this can be represented with m into r power e format. So how the two representation, single precision representation and double precision representation can vary for the IEEE notations. The single precision and double precision majorly vary the memory occupancy. So here the single precision can be represented by using total 32 bits. So here, while representing the floating point numbers, three parts must be represented: the sign, exponent and mantissa. The sign can be represented by using a 1-bit value, and the exponent can be represented with the help of 8 bits. The remaining in the total 32 bits is the 23 bits. These 23 bits can be used to represent the mantissa value. So the total 32 bits of representation can be divided into 3 parts: the sign bit of 1 bit, and exponent of 8 bits, and mantissa of 23 bits. So this type of representation is referred as single precision representation. Now consider an example how this single precision floating point numbers can be represented. So here this is the sign part, and this is the exponent part, and this is the mantissa part. So a single bit can be used to represent the sign. So here the sign can contain the one value which represents the number is a negative number, and the exponent is 1 later on followed by all are zeros. So which is equivalent to decimal number of 128, the exponent value. And the biased by 127, 128 minus 127 is 1. So the mantissa can be represented here with the remaining bits of 32 bits. So this is the mantissa value. So this mantissa value has to be normalized so that 1.01, so which is equivalent to 1.25 in the decimal equivalent. So finally, how this number can be represented means 1.25. So the sign bit is representing the negative number. So minus 1.25 into 2 power 1. So in this way, the single precision numbers can be represented. Next, double precision representation. So the double precision representation can occupy the memory of 64 bits. So here also these numbers can be again categorized into 3 parts of representation. One is the sign bit, second one exponent, third one mantissa. Here the sign bit can occupy 1 bit, and the exponent can occupy 11 bits, and the mantissa can occupy 52 bits. So in this way, the double precision representation can be represented. So these are the two parts how the single precision and double precision numbers can be represented. Now we have to consider how the floating point arithmetic operations like addition, subtraction, multiplication and division can be carried out. So the floating point arithmetic can be somewhat complex than the fixed point arithmetic. Why? Because the floating point arithmetic on a computer is different than in a continuous mathematics. So in mathematics, all numbers can be considered exact. On a computer, many numbers cannot be represented exactly with a finite number of bits. So all calculations are performed with the limited precision. So that's why the floating point arithmetic can be complex, and few algorithms are used for floating point arithmetic operation, addition, subtraction, multiplication and division. So how the floating point addition and subtraction can be carried out with the help of the addition subtraction algorithm. So adding and subtracting two floating point numbers requires first an alignment of radix point. So alignment can be taken place. Since the exponent parts must be made equal before adding or subtracting the mantissa. So both the numbers that are considered for addition or subtraction can be represented in the floating point standard representation of mantissa into radix power exponent form. And before adding or subtraction operation, the exponent values must be made equal. This alignment is carried out by shifting one mantissa while its exponent is adjusted until it becomes equal to the other exponent. How this normalization can be performed means with the help of shift operation. So we have to shift left or shift right in order to get the exponent values equivalent before performing the addition or subtraction. What is the register configuration for storing these floating point numbers for performing various arithmetic operations? So three registers are majorly used. They are BR, AC and QR register. So here each register is again subdivided into two parts. So the mantissa part has the same uppercase letter or symbol as in fixed point representation. To represent the mantissa, the same capital letter representation can be used as in fixed point representation. But the exponent part may be used corresponding lowercase letter or symbol. So here to represent the floating point representation, the two parts mantissa and exponent can be considered. So the register can have two separate parts to represent the mantissa, and the mantissa is generally represented with a capital letter, and the second part is representation of exponent. The exponent is generally represented with a lowercase letter symbol. So assuming that each floating point number has the mantissa in signed magnitude representation and a biased exponent. So in this way, all the three registers, the BR, AC and QR can be represented. So BR is divided into BS and B and small b. BS is to represent the sign bit, B is the mantissa, small b is the exponent. Similar way, the other two registers QR and AC can also be containing the sign bit, mantissa, that can be represented in capital letter, and the exponent that is represented in a lowercase letter. So this is the register configuration for the floating point representation. So this is the AC register. AC register, the sign bit is represented with AS, and capital A is to represent the mantissa, small a is to represent the exponent value, and QR is represented with QS, the sign bit, and Q is the mantissa, and small q is the exponent of the number that is stored in the Q register. Similar way, BR, so here BS is the sign bit, capital B is the mantissa of the BR register, small b is the exponent of the BR register. Here the addition can be performed with parallel adder and comparator in order to check the signs and zero values. And if at all any extra bit that is generated during addition can be stored in the E flip-flop. So this is the register configuration for addition and subtraction. So what are the steps in addition and subtraction algorithm? So during addition or subtraction, what are the two floating point numbers that are considered can be stored in the AC and BR registers respectively. So the sum or difference is formed in the accumulator register AC. And there are majorly 4 steps in the addition and subtraction algorithm. During the first step, check for the zero values. Second step is align the mantissas. Third step, add or subtract the mantissa. Fourth step is normalize the result. So these four steps are the basic steps in the addition subtraction algorithm. Now consider an example that two numbers x and y both are representing with the mantissa capital A, capital B, and small letters of A and B can be used to represent the exponents. So the numbers that are considered are 0.9505 into 10 power 3, and the second number y is 0.8200 into 10 square. So here the mantissas can be represented with capital A, capital B, and the exponent can be represented with small a, small b. Capital A, capital B values can be 0.9504 and 0.8200 respectively. Small a, small b values that are considered are 3 and 2 respectively. So here four steps are major steps in the addition and subtraction algorithm. The first step is check for zero. So a floating point number cannot be normalized if it is zero. The zero value numbers cannot be normalized. So if this number is used for computation, the result may also be zero. Instead of checking for zeros during the normalization process, which we cannot check at the beginning, then the result can be, there is a chance of occurring of result 0. So terminate the process if necessary, if it all the zero value can be obtained during this first step. The second step is align the mantissas. The mantissas associated with smaller exponent is shifted according to the difference of exponent determined while checking the zeros. So in order to represent the exponent values both are equal, the normalization can be performed. So here the first number that are considered in the example can have a e value of 3. The second number can have a e value of 2. So the second number can be normalized. So with the help of shift operation, so that the exponents can be both be equal to 3. So that's why the second number after normalization can be 0.08200 into 10 power 3. So this is the second step, align the mantissas. Add or subtract the mantissas. The mantissa values can perform the addition operation. Next, normalize the result so that shift operation again to be performed. So the result can be represented 0.1324 into 10 power 4. So these are the four basic steps in the addition and subtraction algorithm. Now what are the flow chart for representation of this addition and subtraction algorithm? So here we have to perform the four steps in the addition and subtraction algorithm. That is, the first step is check for zeros. The second step is align mantissas. The third step is mantissas can be added or subtracted. The result can be normalized in the fourth step. So here after storing the two numbers in the BR register, and here we have to check whether the value that can be contained is 0 or not. So during this step, and here aligning the mantissa can be done with the shift right operation so that the exponent values can be both can be equal. In our example, we are shifting right the value of the second number so that both numbers can have the equal exponent value of the 3. Next, during the third step, we have to perform add or subtraction. The addition can be performed directly and the subtraction can be performed with 2's complement addition. So the e value can be checked so that the normalization can be again performed on the result with the help of shift right operation. So in this way, the addition and subtraction algorithm can be performed. The fourth step operation, check for 0, align mantissas addition or subtraction, next normalization of the result. After addition and subtraction, the floating point multiplication algorithm. The floating point multiplication algorithm contains the 4 parts or 4 steps. One is check for the zeros, add the exponent, multiply mantissas, normalize the product. So if it all check for 0, then if the numbers that are considered are 0, the multiplication can be, the result can be 0. So during first step itself check for 0, and if the number contains the value 0, that can terminate the process. So after that, the exponents can be added and multiplication of mantissas can be carried out. So the floating point result can be normalized in the fourth step. So this is the flowchart for multiplication algorithm. The multiplicand and multiplier can be stored in BR and QR registers. The product can be available at the end in the AC register. So this step can be the first step. It has to check for zeros. Otherwise, the result can be 0 if the number that is considered is the 0. So the first step can be carried out here. Next, add the exponent. So here, the add the exponent can be carried out, the second step. Multiply mantissas, the third step. And the fourth step is normalizing the result. So here normalization can be performed with shift left operation. So in this way, the floating point multiplication algorithm can carried out with 4 steps. Next is floating point division algorithm. So here the floating point division algorithm contains 5 parts. One is check for zeros. Second one, initialize registers and evaluate the sign. Third step, align the dividend. Fourth step, subtract the exponents. Fifth step, divide the mantissas. So here this is the flowchart for division algorithm. The AR can hold the divisor value. AC can hold the dividend value. The first step can be check for zeros. If any number contains the 0 value, can terminate the division process. The second step here can be the initialize registers and evaluate the sign. So the sign can be generally checked with the exclusive OR operations. And next, third step can be the align the dividend. So depending upon the value that is obtained in the E, the dividend can be adjusted based on the whether the number is A is the two numbers that are considered is greater than or less than. And here the third step can be the subtraction can be performed on the exponent with 2's complement subtraction method. Next, divide the magnitude of mantissas as in fixed point numbers. So these are the basic steps during the division. So in this video, I will discuss regarding what is floating point numbers, how they can be different from fixed point numbers, what is the standard notation used to represent the floating point number, how various arithmetic operations on the floating point numbers can be performed with various algorithms. And the references that are used in this video are Computer Systems Architecture, a textbook by Maurice Mano, and Computer Organization and Architecture, textbook by William Stallings, and third one is the web reference. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.